I'm going to tell you about shock waves in plasma, and especially in a collisionless plasma, and the way they depart from what you would expect from magnetohydrodynamic. So that's work that's been done in collaboration with Colby Haggerty from Hawaii, Damiano Caprioli from Chicago, and Ramesh Narayan from Harvard. So here is my outline. First, I will introduce the topic and talk about the differences between shock wave in a fluid and the shock waves in a collisionless plasma. Then I will review some results on how do you form a collisionless shock, and then how do magnetic field impact collisionless shocks. So let's go. So now I'm talking about the good old shocks, I would say, in the fluid, what you can find in Zajdovich and Reiser or Landau-Lipschitz. So how do they form, for example? I'm going to take the laser pointer, okay? So a wave, for example, is to steepen a sound wave. So we know that if you launch in a fluid a large amplitude sound wave with a delta P, which is not small, then the profile is going to steepen with time and you're going to form a shock, okay? You can also bump some fluids into each other, like here. So the guy from the right goes to the left, the guy from the left goes to the right, and you will have two counter-propagating shocks here. Okay, so these are the fluid shocks. Something else, still for, oh, I think everybody should mute just to avoid. Also another result which is quite known, still for the good old shocks in the fluid. In the fluid approximation, usually we treat the shock front as a discontinuity, but in the real life, it's not a discontinuity. And the width is a few mean free paths. And why? Because if you are a fluid particle from the upstream and you go to the downstream, okay, the only microscopic mechanism you have to convert part of your directed kinetic energy into heat, which is the undirected kinetic energy, are the collisions with the other particles. And so that's why the shock front has a finite thickness, which is a few mean free paths. Something else also, because of collisions, you have isotropic pressure in the upstream. And so when all the matter, the momentum and energy goes downstream, even if temporarily at the crossing of the front, you may have some anisotropy of pressure developing. Quickly, the collisions are going to restore isotropy downstream. And so once you know that you have isotropy upstream and downstream, you write the conservation equations and you derive all the jumps in density, pressure, temperature, etc. Okay, so that's the usual business for shocks in the fluid. Something else, finally, you can put an external magnetic field however you want, superimpose on a fluid shock, and the shock wave is not going to care because the fluid is neutral, okay? So it doesn't care about the magnetic field. So here I just wrap up. You can form a shock wave in a fluid by bumping and also steepening a shock wave. Pressure is isotropic, magnetic field you don't care, and the front thickness is a few mean free paths. So what's going on here? Here I take you to the solar system. This is the bow shock of the Earth magnetosphere in the solar wind. The sun is here to the left. Of course, it's not to scale. And in situ measurement showed us that the width of this is a shock wave. The width of the shock wave is about 100 kilometers. So based on what I just said, if you reason as if you were in a fluid, you should guess that the mean free path here of a proton, for example, is about 100 kilometers. And not at all. The mean free path is 1 million times larger, 150 10 to the 6 kilometers, which is the Sun-Earth distance. And so what's going on? Here you see that the mean free path is much, much larger, 1 million times larger than the shock front. And so here we are witnessing a collision-less shock, which is only possible in the plasma because the shock is not sustained by binary collisions, but it's sustained by electromagnetic collective effects. So I will come back to it later. So simply put, collision-less means that the mean free path is much larger than the size of the system, the size of your experiment, for example, or the size of the box, or the size including, of course, the size of the shock front. So simply put, collisionless is this. So where do you find collisionless shocks? I just showed you one that we can almost touch in the solar system. In some scenarios of gamma ray burst, here you have a collisionless shock, and here you have another one. In other scenarios of fast radio burst, another astrophysical curiosity, you have here a collisionless shock, and here another one collisionless shock. A safe exception, shock waves in astrophysics are collisionless because the mean free paths are huge. But also in inertial nuclear fusion, here I put you two papers, one from 2020 and the other one from 2017, when people talk about the role of collisionless shocks in inertial fusion. And what we're going to see is that to form a collisionless shock in the plasma, you can't rely on bump. Bump is just another word for close collisions, but you rely on plasma instabilities. The pressure may not be isotropic. Magnetic field, you do care. And as we just saw, the front thickness is much larger than the mean free path, almost as much as you want. So I will now dwell on how do you form a shock, a collisionless shock, and also the pressure, anisotropy, and the role of the magnetic field. They are kind of linked, at least in what I'm going to present to you. So first, how do you form a shock? And I think another good illustration of how do you get some dynamics through collective interaction can be found in astrophysics in the encounter of two galaxies. So here you have a Hubble picture of two galaxies, quote unquote, colliding. And in fact, they don't touch. Why? Because in a galaxy like the Milky Way, you have a star every 4 or 5 light years in every direction. And a star like the sun is really small compared to this distance. So the light takes 4 or 5 years to get to the nearest star, but light takes 1 second to cross the sun. So you see that the sun is really small. So here it's roughly the same distances. And so when these two galaxies, they just go through each other, the stars, they don't collide. They are really far from each other. But the reason why you have a dynamic, the reason why something happens and the two galaxies just don't go through each other without nothing happening is because you have a long range Newton potential in 1/r. And if you replace these galaxies by collisionless plasmas, you don't have the Newton potential, you have the Coulomb potential, but which is also in 1/r. And so it gives a picture of how can you can have a dynamic with just a long range interaction. Another view of this is the following. Imagine, and I think it's to scale. Imagine that you have three cars, again, 2 cars in the Sahara, and they cross each other. If you get a car crash, you're really unlucky, okay? But if the cars, they are electrically charged, they are going to attract each other, and you will have some dynamic of the encounter through long-range interaction, but not close collisions. So what happens if you do what I showed at the beginning for 2 fluids, but now you have collisionless plasma? So they just at the beginning pass through each other, okay? Because you don't have close collisions. But what happens now is that here in this overlapping region, part of the plasma goes to the left, part of the plasma goes to the right, and this is a counter-streaming system, and it is notoriously unstable. Okay, and so if you perturbate, and it's unstable to many instabilities. If you perturbate the system with a wave vector, a perturbation with a wave vector along the flow, you get the famous two-stream instability, which is almost in every plasma physics textbook. But it was found by the end of the 50s that if you perturbate in that direction, it's also unstable. And this, depending on who writes the paper or the textbook, it's called filamentation or Weibel instability. And also, if you perturbate with a K oblique direction, it's unstable. And what happens is that all these instabilities, they are triggered when in this system. And the fastest one is going to win, I would say, the linear race. So here you have some references when we dealt with the hierarchy of these instabilities. But here the bottom line is that some instability is going to grow, to saturate, and so generate a turbulence. And as a result, the flow which keeps entering here, okay, is going to be deflected in this region, and it's going to be stopped in this region, just by the turbulence. And so if material keeps entering, that's just common sense. If material keeps entering, but stays there because of the turbulence, then the density is going to increase, okay? And it's going to increase until it reaches the Rankine-Goyo density, and then you will have one shock to the left and one shock to the right. So you see that the basic ingredient of the shock formation are here plasma instabilities. So I'm going to show you a particular cell simulation that just produced this kind of shocks. So again, it's going to simulate this, but it's going to also just to simulate half of the system. Why? Because if the two plasma shells that quote unquote collide are identical, then the whole system is equivalent to plasma bouncing back against the wall and interacting with itself. Okay, and the reason why people do this is so you save half of the computing time. You don't have to compute what's going on the left side because it's the same. And so the simulation I'm going to show you is this right part. So here in this simulation, you have the plasma coming from the left, bouncing, coming from the right, sorry, in that direction, bouncing back against here the left wall, and here just starting to interact with itself. So all this part of the plasma is not shown, just for clarity, okay? And here in the lower left corner, you have the beginning, the very beginning of the interaction of the plasma with itself. And so you see that the plasma alone is by default density 1, okay? And at the very beginning of the interaction, the two plasma, they just overlap. And so the density is 2. But now I'm going to launch the movie. And what you are going to see, it's really quick at the beginning. The instabilities, they just develop. This density of 2 is going to quickly rise to 3 point something, which in this case is the density of a strong shock. So here is the movie. And you see it was really quick at the beginning, but here you see a beautiful shock wave with a density just of 3.5 propagating to the right. Here you see that the front is not a discontinuity because we work at the microscopic scale, so we resolve the shock front. And also because we are in the plasma, you have electromagnetic field which are created especially near the front. And so you see we have some magnetic energy which rises around the front and dies out as you go to the downstream. So I'm just wrapping up this part. You form a collisionless shock not by bumping materials with each other because you don't have close collisions, but by plasma instabilities. And here you have a paper outlining the full theory. Okay, so now I switch to the second part of my talk, what can happen if you put a B field on a shock wave. So it's been a long time since in magnetohydrodynamic, people worked out the effect on the external magnetic field on a shock wave. But here, magnetohydrodynamic finally, eventually, is the plasma version of a fluid theory, and it still assumes isotopic pressure, and it still assumes cross collisions. Okay. Now, the bottom line, the physical bottom line of what I'm about to say now is that in a collisionless plasma, a magnetic field can sustain a stable anisotropy, and that's the whole point. Okay. If you have collisions, anisotropy is quickly going to relax to isotropy. But if you don't have collisions, a B field can sustain a stable anisotropy. So what do we have here? I'm going to explain this plot, okay? Some decades ago, I think ESA or NASA people, I don't remember if it were the Americans or the Europeans, sent a spacecraft in the solar wind, which was called WIND, I think, and it performed millions of measurements. And in each location, it measured the local magnetic field, okay, the parallel temperature of the ions, of the protons, and the perp temperature of the protons, and the density of the protons. Okay, so with these four numbers, you can first compute the beta parameter, which is the heat energy, thermal energy in the direction of the field, divided by the field energy. Okay, so that's kind of a famous parameter, dimensionless parameter in this community. And on the vertical axis, you have the anisotropy parameter, which is T perp over T parallel. So if T perp over T parallel is 1, it means you have a perfect isotropy. And you see that given the definition of the beta parameter, when the field is small, you go to the right, okay? And you see that even in a collisionless plasma, if you go to the right, your collisionless plasma is isotropic. Why? Because it was found in Weibel in 1959. If you don't have any magnetic field, an anisotropic plasma, even if it's collisionless, is unstable. So here you find another instance of plasma instabilities playing the role of collisions. That's kind of a general pattern. But now, when the B grows, you go to the left, okay? And when you go to the left, you see many points. So what are these colors here? Once the spacecraft computed, measured these millions of measurements, people computed these two numbers, okay, the beta parameter and the T perp over T parallel, and put some points in this graph. And the redder is the point in this graph, the more measurements you add corresponding to this data, okay? So you add, you see where the redder part of the plot, you add many places in the solar wind with these parameters. But here in the upper right corner, you don't have anyone. And why you don't have anyone? Because there is a famous kinetic micro instability in plasma, which is called the mirror instability. And if you plot the threshold of the mirror instability, it fits pretty well this frontier. And so you see that's a beautiful, I would say, confirmation of plasma, of the Vlasov theory of plasma instabilities. Here, all these points are unstable, and so you find no one here. And the reason why you find no one here in the lower right corner is because you have another famous plasma instability, which is called the Fayerose instability. And why you don't have anyone here and here? As far as I know, I've checked 2 years ago, 3 years ago, it was still an open issue. But the bottom line is that you see in all this range of beta parameter, you have a window of stable anisotropies. So a plasma can perfectly be here, If the beta is, if it's here, the beta is too low, it's unstable. But if it's here, the beta is high enough and it's stable. Okay, and that's the reason why in shock waves it's going to have an effect. So what's going on? This is, I would say, the physics of what I'm going to explain. Let's say you have a collisionless shock. So here you see, just to simplify the drawing, I represent the front as a discontinuity. And let's say you have a B field which is oriented this way. So I assume the upstream is isotropic. So you have a temperature, the blue temperature parallel to the field, and the orange temperature perp to the field. And so this guy here upstream is going to go downstream, okay? And given just the motion, you can picture the crossing of the front as if the plasma were compressed, because between these two virtual walls, they are not real walls. It's just a way of viewing the process. And so when the plasma goes downstream, you see, since you compressed the plasma in the horizontal direction, the T parallel went up, but the T perp stayed the same. And so you end up with this in the downstream, right after the shock front. You end up with this configuration. And the question comes, is it stable or unstable? If you had collisions, it would be unstable, okay? But here you don't have collisions and you have a B field. So if the field is strong enough, that can be stable. The field can be strong enough to stabilize this. And so you write the conservation equations. I'm not going to enter too much into the math, and you compute the density jump. Now, if the field is too small, then the field is not strong enough to stabilize this. And so this configuration is to move to an instability threshold where it is stable with that field. And again, you write the conservation equations, and again, you get the density jump. So here I just come back a little bit, but more technically on what I just said. That's the stability diagram of the downstream after the front crossing. So here you have the beta parameter. Here you have the anisotropy parameter. And in all the orange region, the downstream is stable, okay? Up there, you have the threshold of the mirror instability. Down there, you have the threshold of the Fire-Roos instability. So if T perp didn't move and T parallel went up, you land somewhere on this line, okay? If the B field is strong enough so that you are in the red region, you are stable. That's the end state of the downstream. If you landed in this green region, then the plasma is going to move to the instability threshold. Okay, and you don't care about how it moves because the conservation equations determine everything. So just to quickly explain how this anisotropy makes its way into the conservation equations. Here you have conservation of matter, momentum, and energy. So these are the expression for the upstream. These are the expression for the downstream. And in the downstream, the anisotropy makes its way in two places. First, when you think about it, the pressure here is the pressure parallel to the flow, because that's the component of the pressure that pushes the plasma to the front. And also, inside the internal energy of the downstream, you can split up the three components of the pressure. And so if the pressure gets anisotropic, inside U sub 2, you will have some differences. And so what is the result? You can compute the density jump of your shock in terms of the magnetic field. So I'm sorry to introduce yet another dimensionless parameter, but this is the dimensionless parameter used by people who do peak simulation of collisionless shocks. Now here, contrary to the beta parameter here, the field is upstairs, you see. This sigma parameter is the field energy divided by the upstream kinetic energy density. So if you have a strong shock, which means upstream temperature equals 0, you see that this model gives you a jump which comes from 4, which is the jump of perfect fluid in a strong shock in a perfect fluid. But then as sigma grows, you go down to 2. And what's interesting is that what MHD tells you, so MHD is a fluid theory, including some plasma effects. But MHD tells you that in this configuration, for a field parallel to the flow, the jump is always 4, okay, regardless of the sigma parameter. And so you think that there is a big difference between what MHD tells you and what I would say the field-dependent density jump tells you. So we wanted to check this model through peak simulation. So they were done by Colby Haggerty and Dameno Caprioli. That's a really recent paper in MNRAS, monthly notice of the Royal Astronomical Society. So here you have in the horizontal axis the sigma parameter, it's a log scale, okay. Here you have the density jump. The theory I just showed you gives this dashed line. And you see that the peak simulation, they reproduce quite well the theory. And you see a transition around sigma equal to 0.11. And indeed, the density jump goes to 2. We wanted to check that because the density goes to 2, we didn't have just an overlapping of the two plasma shells, but we had a shock. And to check this, what you do is you compute the entropy jump. So since in the theory we work at the kinetic scale, we work from the distribution function. In the peak simulation, you can also have access to the distribution function, and so you can compute the entropy from first principle, which is minus integral of f log f. You see in these dimensionless units, the entropy jump 0 here correspond to no shock. And you see that the theory, the dashed line, gives you a shock all the way through strong sigmas, since you do have an entropy jump. And again, the squares in colored are the peak simulation. And again, it fits quite well, the theory. And what about this point here for really strong sigma, sigma equal 10? Why is it so low? So I will explain to you. In the theory, we assume downstream a bi-Maxwellian, which is a Maxwellian with 2 different temperatures depending on the direction, okay? When the field gets strong, it takes some time for the bi-Maxwellian to establish in the downstream. So here, for sigma equal 5, the bi-Maxwellian in the peak simulation had been established. We waited long enough. Here, for this strong field case, we didn't wait long enough, and the referee didn't care, I would say. And so we still have this point here. But if we would wait long enough, this point here would raise and come to this dashed line here. So I don't want to tell much more on this. So here I wrap up. You see that in a collisionless plasma, to create a shock, you cannot rely on collision, so you rely on plasma instabilities. The pressure in the collisionless plasma can be anisotropic if the field is strong enough. And this is why the density jump of a shock can go down. And again, that's from the beginning, the front thickness is going to be much, much larger than the mean free path. So here I wrap up the end. Are there some open issues? Is what I just told. Regarding the shock formation, I don't think so. I think that the basic ingredient are plasma instabilities, and I think no one expects any surprise here. Now, regarding the role of magnetic field in the density jump of the shock, I just showed you what happens if the field is aligned parallel to the direction of the flow. The question is still open, what happens if the field is oblique? And also what happens if you are relativistic? So there are much more open questions here. And most of what I've just said, all the reasons why collisionless shock can depart from MHD is detailed in this sort of review paper I wrote 2 years ago in ABJ, Astrophysical Journal. Can we trust MHD jump condition for collisionless shocks? So I'm done, and thank you very much for your attention.